All right, back again. We have some final topics that I'm going to cover here in this next video. So the other video finished with um, constructing the inscribed and circumscribed circles of a triangle. We're going to get into some other stuff this video. I want to go back and mention that no matter what triangle we draw, we can always inscribe a circle in it. We can always circumscribe a circle around it. Okay, that's a guarantee. But when we work with a quadrilateral, that is not the case. Some quadrilaterals will not be able to be inscribed in a circle. What do I mean by that? Well, some quadrilaterals, all right, you won't be able to find a circle that hits. You'll be able to find a circle that hits 3 of the 4 points, but sometimes you'll miss that 4th point. So that's unlike triangles. Triangles, you can always inscribe a circle, you can always circumscribe a circle, but you cannot for quadrilaterals. Now there's some special cases when we can, some special cases and properties that we need for when we can inscribe a quadrilateral in a circle. Okay, so that's what we're going to go over right now. I'm going to go back over to Geometry Sketchpad quick and show you what I mean. Okay, so right here, what we have is, a situation where a quadrilateral does in fact fit inside of a circle. A single circle will be able to hit all 4 points. Okay, that's not always the case. You will not be able to do that for all quadrilaterals. Okay, for a rhombus, where the angles, let's say that for a rhombus where the angles are not 90 degrees, we won't be able to fit it. We won't be able to hit all 4 points with one circle, and we'll show that in a little bit later. Okay, so back over here, what I wanted to show you was the properties of the angles that will allow us to inscribe a quadrilateral into a circle. Now, the concept it's going to be related to is what we talked about in the circles chapter, is inscribed angles. So let's go back and recall what that was. An inscribed angle, if you have a circle, okay, an inscribed angle was an angle whose vertex was on the circle and its sides were 2 chords. Okay, now here's what happened. If we knew the arc measure from, let's call it point A, from point C around to A, okay, let's say that was a 220 degree arc. What we know is the measure of the inscribed angle that opens up or intercepts that arc is half. So that is going to be a 110 degree angle. Okay? And we know that. And that's the concept that we're going to use here. So what I want you to focus on is, let's go back up here. I'm going to focus on angle A right now. It is in fact an inscribed angle. Its sides are chords of the circle. And it opens up to arc BCD. All right? Now let's make up, I'll just make up a number here to work with, and then we'll come back and we'll work with non-numbers. So let's say it's just 140 degrees and make it simple. To get angle A, we know it would be 70 degrees. All right, now here's the relationship right here. If you look at points B and D on this arc, you'll notice that angle C is also an inscribed angle, but it opens up to the arc that goes in the other direction, goes around the circle the other way, so from D around to B. Well, if you know that the full circle is 360 degrees, we take away 140 degrees that we use to go this way, that leaves us with 220 degrees, right there. Now, angle C is an inscribed angle that opens up to an arc that's 220 degrees. 220 divided by 2, that's 110. Now, there's a relationship between these two angles that are across from each other. You can see right now that they add up to 180 degrees. And that's not a coincidence. Here's the idea. The entire circle is 360 degrees. Inscribed angles are half of the arcs that the measures are half the measure of the arc that it opens up to or intercepts. So basically half of 360 is 180. You're going to have the entire circle all the way around, right? 360 degrees. This inscribed angle is going to take up part of that circle. The angle across from it is going to take up the rest. So no matter what these two are, they have to add up to 180 because they're going to take 360 degrees and we're going to cut them in half. Now, let's say we go and we use the other two angles. So let's erase some of this stuff. And all right, it doesn't matter what angle we start with. Okay, so we will make up an arc angle measure. I don't know, 190 degrees. From here to here, it looks like it's about 190 degrees maybe. Okay, let's just say it is. We're going to take half of that, and that's going to be 95 degrees. Okay, because this angle is an inscribed angle that opens up to arc CA. Now, how do we figure out what angle D is? Well, angle D is an inscribed angle that opens up to the rest of that circle. So 360 minus 190, that's going to get us 170 degrees. So from here all the way over to here, 170 degrees. And of course, half of that, what do we got, 85? 85. And it's no surprise that these two add up to 180 degrees. Okay, so it won't make any difference. We can actually prove that concept, using algebra, but I think you get the idea. If they make us prove it, okay, it would be a kind of a lengthy process, but we could do it. All right, let me just try to do this really fast here. So I'm going to just I'm going to cheat a little bit here, sketch a circle, and it doesn't make any difference. We'll make it look like that, right? Okay. So there it is. We'll call this A, B, C, D. What I'm going to do is I'm going to prove that the measure of angle A plus the measure of angle C must be 180. Okay? Basically, opposite angles of a quadrilateral that is an inscribed in a circle must add to 180. Must have measures that add to 180. All right, so again, I'm basing my entire proof on the concept, okay, that the entire circle, okay, to go around the entire circle, arc measure is 360 degrees, okay? Inscribed angles have measures that are half of the angle they open up to. Sorry, arc angle measure. that they open up to. They intercept. Okay, so that's the concept right here. All right, what I'm going to start with is the measure of angle A is going to be half the measure of arc. Now, I'm going to throw this C in there, not that I have to. Technically, it's got to go counterclockwise, but I'm going to just throw the C in there. The measure of angle A is half the measure of arc BCD. Measure of angle C, using our inscribed angle idea, is half the measure of arc, and let's go this way, DAB. All right, so we'll come back to that. Now, the measure of arc BCD plus the measure of arc, what is it, DAB, is 360. That's because it's the entire circle, covers the entire circle. Now, half of that, if we take half of all these, you're going to multiply it through by a half, basically. All right, half of 360 is 180. Well, now, by substitution, this is the measure of angle A. Sorry. This is the measure of angle C, and it must be 180. And that's by substitution. So that's how we can establish that if they were to ever ask us to prove it. I doubt it, but they could. Now, be ready for a part 1 question. They could ask something about, this right here. They could call this 3x, and I'm just going to make it up so it could be ugly. This could be 2x minus 10, okay? What would you have to do with those? Well, don't set them equal. Make sure you add them to 180. Okay, and then solve. So that's the type of problem you could face on a part 1. Okay, so you should do something like this. And I seriously doubt they're going to give us a proof. So be ready for a question like this. And what is that? 38-ish? Yeah, I'm going to guess 38. And then if they ask you for the angle measure, of course, you just plug in, do what you got to do there. Okay? All right, something seems wrong. Yeah, that's good. That's perfect. All right, so that covers the properties of angles. Oh, it does say prove properties of angles for a quadrilateral. So, yeah, I guess they could do that. They have never made us do that proof before, but now you can see what to do. All right. As far as these topics go, we took care of that one. These are all mini topics in here that we've covered. Okay. And then this one's a little weird. We're going to actually talk about that one, even though it should not be tested. They have actually tested on those, those standards that are supposed to be for more advanced. All right. Let's say we have a random point outside of a circle, okay? And what we wanted, and we have the center. All right. We want to find a tangent to the circle that also passes through this point. Very complex concept. Here's what you have to remember, and this is going to be extremely tricky on this one. Go back to your concept list. If we had a circle and we established diameter AB on circle O, let's say, no matter where we place C, if you remember from our concepts, angle C must be a right angle. And we established this because it opens up to a semicircle, right? Inscribed angle that intercepts a semicircle. Must be a right angle. Now, this is not easy. That's the concept we have to use. Okay, we're going to have to construct that using this concept, but we can't use this circle. We're actually going to have to connect this center to this exterior point. We're going to have to construct the perpendicular bisector. This is crazy. Construct the perpendicular bisector. Still not done yet. Now we have to construct the circle centered there. Okay, try to imagine this. And here's what we just found. No matter where we put, now we have this concept right here, right? Let's say this is AB, right? No matter where we put C on this circle, it's going to make a right angle, right? Well, if we put it right here, if we put C right there, that gets us a tangent, because we know a tangent to the circle has to have a right angle with the radius. So that's an incredibly complex idea. But in the construction there, that's what they're looking for, right? We're going to have to construct this line, which should be easy, just use your straight edge. Then the perpendicular bisector, right? We remember how to do that. Then that's the center point for this circle, and wherever that circle hits this circle, that's going to be the location we're looking for. Could be, of course, there or there. Pretty complex, but that's what we're looking to do. I'll take you over to Geometer Sketchpad again, and because I can't show my compass tool on this, so I'll be right back. Okay, here goes. So here we have it. Let's call this, let's see, label point. Now we're going to label it point O. And let's just call this point B. All right, so what we're going to do is we're going to try to find point A. It's going to be tangent to circle O and pass through B. Not an easy concept. Okay. What we have to do first with our construction tool is pick a radius. Okay, we're going to construct a radius here that we're going to use. Now, when we put our compass tool here and use the radius we choose, we're going to use the same radius here. What we have just done is created the perpendicular bisector to point OB. Segment OB. Now, all that did was that established the center point of O to B. Okay. Now, we could clean that up a little bit, because this is our original. I'll clean this up and then come back. Okay, back again now. All I did was get rid of some of that mess. Really, this is the work that you're going to have to show. You drew in OB, the segment, okay? And what we're going to do is, we constructed the perpendicular bisector using our center of our compass tool here and this radius, right? Then we came over here, center of our compass tool on B, drew this radius. Wherever those connected, those intersections, this line right here is the perpendicular bisector of BO. All right. That just gave us a center point, really. You just can't erase any of this work. Now, I'm going to take my compass tool, put the center of it there, and then I'm going to draw that circle that opens up here. All right. Now, that is our key concept here. Let's make it a different color. All right. Anywhere on this circle, okay, if I connect to anywhere on this circle, let's not forget our concept here. anywhere on this circle, I'm going to establish a right angle. Okay, that's going to give me a right angle. But what's missing is I chose a random point here, okay, and it's not touching the circle, so it's not tangent to the circle. Well, what do I want to do instead? Let's get rid of that one. That one's no good. Instead, I want to take a point that's on this circle, but also on my original circle. And the idea behind using a right angle is now this angle right here is going to be a right angle because the fact that we have a diameter, right? This inscribed angle opens up to a diameter, semicircle, so it's got to be a right angle. Now, why is this line tangent? Sorry, why is this line tangent to circle O? Because a radius and a tangent to that point of tangency make a right angle. So we got a lot going on there. That's the construction they'd be looking for, and hopefully if we face this, you guys will be ready for it since you watch the videos. Hopefully you've subscribed, get all the updates, and thanks for joining in. All right, actually I've got another concept that I wanted to go over that I like, and we didn't get to this year. Where is that? So we've taken care of all that. All right, let's make sure, before I get to the one I want to do, let's talk about the constant of proportionality as far as radian measure of an angle. Okay, so on your reference sheet, okay, what you're going to get, let me make sure, I'm going to go double check and see exactly. They're going to give you either 180 over pi or pi over 180. Let me just go and look at that quickly. Okay, back again. I went and actually I clipped right from the reference sheet for mathematics. This you get in the back of the exam, so make sure we rip that off and use it. The constant of proportionality that they're talking about here in this standard, constant of proportionality is this idea of 180 over pi. All right, let's talk about why that is the way it is. All right, so we have to define what radian measure is. Radian measure. How we define that, it is an angle measure indicating how many radii the arc length that the angle how many radii the arc length that the angle intercepts or opens up to would meet. Now, let me show you what I mean by that. So, here's a circle, right? Let's say we have approximately, I'm going to try to make it, it's probably more than 1 radian, sorry. But this angle measure right here, theta, we like to call it. Okay, let's say we open up, well, that's actually backwards, but that's okay. What we're saying is, how many of these radii along this arc length, it'd be a little over 1 is my guess. I would need 1 radius to go from here to here, plus a little bit more. So let's just call it 1.2. So this angle measure might be about 1.2 radians. What is a radian? A radian is how many radii we would need to cover the arc length that the angle opens up to. So that's kind of what I'm trying to explain here. It's one full radius to get to about here. Then we need a little bit more. Now, we're just not familiar with this way of measuring angles. It's uncomfortable. You're used to degrees. If you estimated this, you'd probably right away tell me it's about 70 degrees. And I'd say, yeah, that's pretty close. Um, but we just don't understand that that's about 1.2 radians. Uh, it's something that you just need experience with, and you'll be fine once you do. So that's what radian measure is. So how is the constant of proportionality 180 over pi? Okay? And that's what's strange about this. Here's what we say. An entire circle, what we're used to, an entire circle measures 360 degrees. Okay? Now, if we go around the entire circle, think arc length, right? The arc length of an entire circle, is its circumference. So, what I would do is take a look at our circumference formula. It's 2 pi r. 2 pi r. Okay? Now, that's for the circumference. Now, let's assume just for a minute to make it easy, let's use a radius of 1. So, if the radius is 1, to make it easy on ourselves, the circumference is 2 pi. Now, the circumference is also, if you look at an angle measure, arc angle measure, it's also 360 degrees. Okay, so we're really trying to connect here. Now, the constant of proportionality then for 1 radian, right? We need 2 pi radians to cover the entire circle. Why? We need 2 pi radius to go around the entire circle. So we need 2 pi radians will cover the entire circle. Now, how does that come in? Well, a radian, or sorry, 2 pi radians then is how many degrees? Well, it's 360 degrees. So 2 pi radians, 360 degrees. How does that constant of proportionality play in? Well, basically, here's what we look at. If we take 360 degrees divided by 2 pi, that's your ratio of degrees to radians. Well, somebody just reduced this, right? 3 times 180, 2 times pi, knock out the 2's, okay? So, the constant of proportionality is either 180 over pi, or we can always flip it. We can go radians to degrees, pi over 180. So that's something that I think was important to cover. I know we talked about it. I'm sure it didn't totally make sense, and hopefully this helps a little bit. So let's not forget, a radian, what is it? It is a way to measure angles. It'll cover 1 radian. If we just look at 1 radian, let's say this is the radius, right? If we take that radius and cover right about to there, okay, this angle, if that's 1 radius stretched out over there, well, this theta would be 1 radian. Okay. How many radians in a full circle? There's 2 pi. It goes along with the circumference formula, 2 pi r. Okay, so that's what I wanted to talk about today to cover. Let's see, what concept is that? Yeah, that's GC5. Okay, last topic then. This is one that we didn't get to this year that I enjoy. We don't have to prove the area of a circle is pi r squared. It is in the formula sheet, reference sheet. But I think it's a good exercise to show you where that comes from, and it kind of connects to, so see what this connects to. The area is pi r squared. We're going to kind of connect it to limits a little bit. So I want to show you where that comes from. Area of a circle. Again, it's on the reference sheet. We don't actually have to do this. So here's how we almost use a little bit of calculus here. Imagine I took a circle and I made a whole bunch of slices. Let's say we made about, like, I don't know, cut it in half 3 or 4 times. Okay, let's imagine that we did that. Let's say these are all perfectly cut in half, which they're not. And I rearrange these slices, right? I rearrange them. So I put, every other one. I'm going to arrange this way. Okay? So half of these slices will face up, the other half down, and so on and so forth. What did I do? About 16 slices. To do that again. Let's imagine I could actually do a halfway decent job with this. I think I need one. Is that it? 1, 2, 3, 4. One more. Okay, there's 16 slices. All right, what I did was I took these equally, sliced it up, 16 slices, and we rearranged them, this way so that it looks like that. Now, here's the limits. The smaller we make these pieces, okay, the closer, if you can see this, the closer and closer and closer this figure gets to a rectangle. You can see it. As we slice it smaller and smaller and smaller, these slices, as we stack them this way, will approach a rectangle. Now, the area of the rectangle, of course, is, we know it's length times width, right? So what is the length and what is the width? Well, the width is approaching, if you look, the radius of the circle. Now we got to figure out what the length is. We'll come back to that. So the width is approaching the radius of the circle. Wow, this is the next part. What is the length approaching? Well, here's what we got to realize. Half of the slices are facing this way, so to speak. The other half are the other way. So basically, the length is half the circumference of the circle. Well, the circumference of the full circle would be 2 pi r, right? So half of that would be pi r. And that's what we replace the length with, pi times the radius. Hence, pi r squared. That's kind of how we establish the area formula for a full circle. And the area of a sector, it's kind of established the same way. So that's something that could come up, and now you have at least, have seen that concept. And we have covered it. So hopefully you enjoy the videos. Please subscribe and like some of the videos. Good luck on the exam this week. Take care.